Today I would like to present the topics using open source software to build an industrial-grade embedded Linux platform from scratch. I'm AZ Lin, work for Moxa, a Taiwan company, and also a cybersecurity fundamental specialist and Debian developer. You can reach me in this website. Before this presentation, I would like to make a survey. How many people is familiar with industrial platform? Could you show your hand? Okay. So actually, this topic, this presentation is quite difficult for me because I made over 200 slides in my first version. I tried hard and I cut it into 87 slides. So I will try to skim and finish this presentation in time. Industrial platforms such like edge, industrial computing, and network. According to the industrial application variety, such like rail, smart grid, and some energy. And those this type of product is quite wide range. We can have a microcontroller or a server level. So we might have a lot of choices on this. So before using open source software, something we should know. That is copyright pattern. Copyright is very, very important for the open source and which related to the open source license. Okay? Another is pattern. So for the open source copyright, luckily the Linux Foundation created a project named OpenChain. It's identified key recommended process for effective open source management. We can easily to manage our open source via this project. It teaches us how to manage, how to control our usage with the open source. Another is Open Invention Network. It's a shared defensive patent pool that can protect our Linux. So again, we have to take care of open source copyright very carefully. We have to use the process tooling and support. We have OpenChain, SPDX, Fossology. Both of them are Linux Foundation projects. We use OpenChain to control, manage the open source. We use SPDX to exchange the software package. We use Fossology to scan in the license. Okay, back to the topic. Industrial harsh environment, such like rails, grid, transport, factory automation, oil and gas. There are some common basic features, such like longevity, stability, and security. And there are also some advanced features, such like performance, real-time, resource limited, and safety. Beware of that. Some of the features need a special hardware, so we need to evaluate in the very beginning. Okay, this is the life cycle of industrial-grade embedded Linux platform. As you can see, we have a development phase, maintenance phase. In the development phase, we have a system preparation and building and testing. In the maintenance phase, we have a long-term test and regular update. For the industrial product and the platform, it is very important in this phase. That is because the life cycle in industrial platform usually more than 10 years. So we need to take care about the maintenance phase very carefully. In the deployment, in the development phase, as you can see, this is the prototype for embedded device. We have hardware, we have architecture-dependent firmware, such like and some BIOS. And those we have bootloader, kernel, and system call interface inside. glibc, init system, and user application, they are in the root file system. So we have user space and kernel space. First of all, we have to choose the proper bootloader. The bootloader is trying to initiate hardware and load the bootloader inside the DRAM, and then load the second bootloader to initialize others, and then loading the Linux kernel, and then the Linux kernel will decompress itself. So there are some category for the bootloader. Typically, we will use the U-boot in ARM product and the GRUB in x86 product. But for some experts, they will use the core boot or IF find. In kernel, there are two main kernel. The first is Linux kernel, and the second is preemptive RT kernel. The Linux kernel typically are suitable for the performance and the resource-limited target application. Before maybe 10 years ago, in resource-limited application, we usually use the micro C Linux. But in the recently, Linux kernel support no MMU architecture and support the tiny kernel. And those we can use the Linux kernel in some resources limited platform. And for real-time kernel, it's suitable for real-time function safety and resource-limited target application. By the way, I have listed some reference for real-time application, such like Synomine or RTAI. Okay, once we decided the type of kernel, we have to get the kernel. So there are many sources. The first is SOC board support package kernel. That is BSP kernel. So this kernel was provided by SOC vendor. If we use that kernel, it causes some issues like different SOC might use different version of kernel. That means if we have more than 10 SOC, we might maintain 10 versions of kernel in the same time. The most important is that the lifetime is unsure. So let's take a look at LTS, long-term support, long-term stable kernel. As you can see, the Greg and Ben Hutchins maintain 5 kernels here, 5 versions of kernel. So the longest time is about 6 years. It attains the software uptime for stable kernel, only accepts bug fixes and security fixes. But 6 years is not enough for us, especially in the industrial application. So we have another choices, that is LTSI, Long-Term Support Initiative. This is a Linux Foundation collaborative project. It's based on LTS, and it has an auto test framework. It also adds some new features inside the kernel. The next is CIP, Civil Infrastructure Platform. This is also the Linux Foundation collaborative project. We also joined this project because we want to support the Linux kernel more than 10 years. So we have a supportive strategy. We have auto test framework. And our goal is to maintain the Linux kernel more than 10 years. This is also the project in Linux Foundation. So this is a figure that you can see. The Linux kernel, LTSI, and CIP, the relationship. This is the table version. As you can see, the maintenance period, SOC vendor is unknown, LTS 2+, LTSI is 2+, and CIP kernel is 10+. And for the features, The SOC, BSP, and LTS accept bug fixes and security fixes. But in LTSI, it accepts new features. So does in CIP kernel. So the latest version, the LTS kernel is 4.19 and CIP is 4.19, but LTSI is 4.14. For the real-time kernel supported, only CIP kernel support the real-time kernel. So that is the comparison. Just like I mentioned, there are many applications such like performance real-time. Is that mutual exist? Yes, some of. If you enable the real-time, it might decrease your performance. So what if I want to enable a product with different application to fulfill the multiple scenarios? In ARM-based, we can use the FIT, front-end image tree. These formats can support the devices to support different kernel and different application. As you can see, this is an example. You can list your image here and another image below. So we can have multiple kernel, multiple file system in the same product. And those we can configure this product to fulfill the target application. The next is user space. I want to address the ELISA. It's a safety critical systems project. This is also the Linux Foundation collaborative project. This project aims to provide the solution in functional safety application. So it uses CL to Linux MP and real-time kernel insights to fulfill the IEC 61508 standard. So if you are focused on functional safety, you can have a look in this project and CL to Linux MP and real-time kernel. For others, the library, this is very important for the system. There are some open source projects there. For example, glibc, micro CLabC, NG Next Generation, and Muscle. Their licenses are quite different. And as you can see, they also have some different features. For example, glibc supports stable ABI, backwards compatible, and for simple versioning. And some security feature. And for micro CLabC NG, it's mainly to support the no-MU architecture and for tiny size. So if your application is for resources limited, you can consider to use the micro CLabC next generation, this tool. And the Muscle is also suitable for resource limited application and security application. But please be aware of that the year 2038 problem. This is the issue similar with year 2000. The 32-bit system can be reprinted the dates from 1901 and 2038. As you can see, when we get the dates of this time, the integer will overflow in 32-bit architecture. You may mention that they are still 19 years from now, but as I mentioned, the industrial platform usually have a very long life cycle, so we should focus this issue now. Otherwise, it's hard to fix. So when you choose the C library, you should consider this problem also. Okay, next, the Init system. Init system is the first application which will be executed by the kernel. It manages the application and services. There are some open source tools here. For example, BusyBox, SysFinit, systemd, OpenRC. Typically, in the past, the embedded system will use the BusyBox because it's very tiny and easy to use. However, the industrial platform connect to internet is a trend. So many devices will use the systemd or OpenRC. So you can choose your own init system depends on your application. So I will also list the C libraries supported. For example, BTBox support MicroC dash next generation and GLabC muscle. And for systemd, only supports GLabC. So if you want to use the MicroC Linux NG, systemd is not suitable for you. The next one is to choose the proper root file system. There are many open source projects to provide the root file system. For example, BusyBox, Yocto, Buildroot, and Debian. You may mention that Yocto is not a root file system. Yocto is just a tool. Yes, exactly. So it depends on the meta layer. It can provide a root file system. So BusyBox contains 300 to 400 applications. So it's not a package. It's just inside the BusyBox. So it could be very tiny, but functional limited. It's also only support the MicroC, LabC, and GLabC. And in Yocto, the famous project in Linux Foundation, the lifetime is only support the previous 2 releases, and the C library only support the GLabC and muscle. For Buildroot, the famous root file system and build tool in embedded system, the maintenance period is only 1 year. The number of packages is more than 2,000. It supports GLabC, muscle, and MicroC, LabC next generation. And the next one is Debian. Debian, the maintenance period of Debian is 5 years for specific architecture. It supports more than 50,000 packages in Debian. It also supports GLabC and muscle. And yeah, there is some myth. You may say Debian is very heavy and very fat, very easy, very hard to customize. That is not true. You can customize a Debian into a tiny profile easily. So we can create a very tiny root file system for Debian in our embedded Linux. So yeah, we have Bootloader, we have Kernel, we have root file system, and something like that. So we have to have system development tools like Yocto, Buildroot, or some Debian specific tools. As you can see, you can use the Yocto to build a BusyBox root file system. You can use the Buildroot to build a Buildroot root file system. You can use many tools to build a Debian root file system. So I also list the toolchain supported here and the license below. So you can choose what you want. And I want to mention that LiveBuild is a very powerful tool for Debian development. Many derivative distributions use the LiveBuild to customize the Debian, such like Kali. Okay, so we use Debian. Why? Because its stability is as a procedure that's unstable, testing stable, scalability from laptop server to embedded devices, and good system security. The Debian has the security tracker, long-term support 5 years, and multiple architecture, and the end is more than 50,000 packages inside. In the build and testing, it's very important for industrial platform. So if you want to get more information, you can check this in reference in the end. This is our testing and development procedure. As you can see, the developer fork the Git and make some changes. After all, they will send the patches to send the pull request. After that, this will jump to CI/CD automatic release pipeline. This pipeline will result the yes or no to our team, and we can know pass or not. This is the CI/CD automatic release pipeline. CI means continuous integration. CD means continuous deployment. So we have a CI, CD, CD, building, deploying, testing, and release. So we use GitLab and Jenkins to monitor the status of the branch. There are some changes. We will trigger the Jenkins. The slave node will do some static program analysis. We use the Jenkins to manage the static testing cases. So, as you know, the Linux kernel is quite large, so we spend lots of time in compiling. We use the distributed compiler to reduce the compile time. This time, here we use ice cream, which is created by Susan. So we use the distributed compiler to reduce our time, and thus we can have more time to do the test. So as you can see, we have the building form. So in the delivery, we use Lava. This is a tool made by Ninaro. We can use this tool to make some deployment to our testing form. Once we get the binary and the image from the Jenkins, we will send a job file via the XML RPC, and it's sent to Lava master. It will dispatch job via 0 and Q. And then we will download the image from the Jenkins and send the image to the devices. The next, we will trigger a test framework, and this test framework will send the test cases and start to test. We have several tests, such like dynamic program analysis and platform test, to ensure our quality of the product. So there is a embedded test framework I would like to address. This is Fuego. Fuego in Spanish means fire. This is a test framework for testing embedded Linux. So LTSI project, which is a Linux Foundation collaborative project, use this framework to make the test. And there are over 100 pre-packaged tests already. So after that, we can get the result and send to the developer. Okay, the next is maintenance phase. In the maintenance phase, we have a long-term test. Long-term test means longevity testing, reliability testing, robustness testing, and security scanning. We have to do this test 24 hours, 7 days, because we have a very, very long life cycle for our product. So the test cases are managed by the test framework. The first is the longevity. It's mainly to test the hardware, so we have endurance and capability test. The next one is robustness. We have a fuzzing test, and I also list the test tool in the end. The next one is the reliability test. We have a power failure test, reboot test, and regression test. You might be curious that why we have to reboot to test our product, because we have several issues before. Sometimes the system will hang during the reboot, and the root cause is that the driver or the application has some deadlock issue in some situations, so it's caused the devices and the platform to be hanged. And the last is a security test. We have a daily test for CVE. So as you can see, we will scan the platform every day to generate a security report. As you know, the last week we have a SACK security issue in kernel. So we can usually to get the result in each platform that is there any CV inside. And for stable kernel maintenance, we will have the kernel CI to test our kernel. This is an automatic Linux kernel testing tool. So it will detect basic, report, and fix a regression on upstream kernel trees before release. We can have more confidence before releasing the kernel. So it's a short test on many configurations. That means we can test many boards, many SoC, many devices via the kernel CI to make sure that each changes is okay. The next one is Reproducible Build. This is a very amazing project. It's also the open source project. It's create an independent, verifiable path from source to binary. It ensures the build have identical results. And then we can prove the source code has not been tampered or modified. It's very important for the security. So I also list the open source testing tool below. You can have some look. So the CI/CD, LT are concepts of software engineering instead of tools or the procedures. Because the tools or procedures could be phased out. So we need to focus on the software concepts of software engineering. Okay, we come to the next step is a regular update. As I mentioned before, the industrial platform, the product, we have a very, very long life cycle. So if we want to update the security issue or some bug fix, we have to update the devices remotely because in the industrial application, the platform usually to put in humanless place. So we need to have the software update to fulfill the demand, like bug fixes, security fixes, new feature over 10 years. At least some component might be updated. For example, the peripheral devices of firmware, bootloader, device tree, Linux kernel, root file system, system configuration, and replication. Typically, we update the application more often, and some Linux kernel depends on the situation. But I also list some risk in updating the software. We fail to update, the devices may become the stone. So I list some requirement here for industrial Linux platform. For example, the hash environment, middle of nowhere, bandwidth limited, multiple versions supported, multiple devices, and longevity. These are normal requirements for the industrial platform. So the media of the software update, we can use a wire cable, OTA, portable storage, or on-site. But typically, we don't use this solution. It's too much cost. I also list some software update requirement here. For basic features, we should have a fail-safe, rollback, size reduction, signature, multiple storage support, your system integration, remote access. For additional features such like online and offline updates, encryption, data updates, successful update detection, and proactive updating. And for the industrial embedded devices approach, we can use the image block-based. It's a quite large size, okay? But it's much simple. And file-based, package-based, and data-based. You can choose what you want, depends on your demand and your application. need to consider the partition architecture here. So you can have some design in your embedded device, and those you can make the best update mechanism. There are some design here, for example, asymmetric and symmetric firmware update. This is the asymmetric firmware update design. This is a symmetric firmware update design. For this design, we will have some downtime because we only have the main OS. But once we get dead, we have a recovery OS. So we have fail-safe. But for the symmetric firmware update, we have backup OS. So we will keep alive always. But the drawback is that we have double copy of OS. So you can choose your design based on your application. So typically, in the very low-end devices, we will use this design. But in some high-end application or devices, we will use a symmetric design. It depends on your storage and your mechanism. So I list some open source project for software updates. The SWW. That means software updates. And IUC OS tree. So software update and IUC support fail-safe and rollback feature. They all also support the Delta updates. Signature for security. They support multiple storage. For Yocto and Build. In my experience, I use software updates because this is very easy to use and suitable for embedded devices. So there are some comparison for others. Software update and IUC support asymmetric and symmetric updates. And they support the image-based and file-based. The license is GPL and LGPL. Okay, this is my conclusion that we have to plan our design and target application. The industrial application is longevity, stability, and security. We need to collaborate with the community, so we use many open source. And last one is, we cannot the best solution, but the suitable solution for our application. That is my presentation. Thank you. So, yep, do you have any question? I'll present very quickly because, yeah, many slides. Do you have any question? Okay, thank you.